Okay, so this is for linear programming. Otherwise, the class that I have or I'm taking for this is called linear nonlinear optimization. So this is going to be a problem on unboundedness when it comes to your system that you're trying to, your objective function that you're trying to optimize and with your constraints. So to kind of go over this, you can actually, I have an example here. So you have you want to maximize this function or this equation where it's x1 plus x2 such that you're given one constraint where x1 minus x2 is less than or equal to 1, such that the two variables x1 and x2 are greater than or equal to 0. So just from kind of looking at this alone, you can actually tell that this problem is unbounded, mainly because it has only one constraint on it. And you can let x1 be any number that you want to as long as x2 is a number, is that same number, subtract 1. So for example, you could let x1 equal, let's just say like 100, but as long as you can still fulfill the restraint if, and this will be the constraint, if x2 is, let's just say 99, right? So that fulfills the constraint of that. However, there's no saying that x2, it can be anything you want it to be, right? It can be you could be 1,000, a million, anything you want, right? So just by looking at that alone, you know that this problem in a way can't be optimized. Anyways, but we'll try and figure that out through the simplex method. Okay, so in order to kind of get this here, let's turn it into a form that we can do the simplex method in. So if you remember, we set our objective function equal to z, and then we put all the variables on one side of the equation and then solve for 0, which is what we did here. So we have z minus x1 minus x2 is equal to 0. And then down here for our constraint, it's already in standard form, the less than or equal to 1. So we just add in our slack variable. So it's x1 minus x2 plus w1 is equal to 1. And then we set all those variables, including our slack variables, greater than or equal to 0, right? So let's try out our simplex method here and see what we get, right? So let's do, we have x1. Yeah, write that a little bit better. I want to get in the way of my video here. So let's do x1, x2, w1. Okay, this is just gonna be a quick one. We have our right-hand side of the equation. Go down, we have our objective function here. Our objective function here was a -1, -1, 0, 0. Our variable on the left-hand side here is going to be w1 because we only have one constraint. So it's going to be x1 is 1, x2 is -1, w1 is 1, and then the right-hand side of that is equal to 1. So traditionally for our simplex method, we want to choose the most negative number, if that makes sense, or the smallest number, and then make the number below that our pivot, right? In this case, we only have one constraint, so we're actually skipping out a method on the simplex method. So let's go to this first -1. If we go to the number below that, it's a -1, so we're not allowed to use that as a pivot because it's a negative number. So we move to the next negative number, which is the -1 here, and we can skip between the two because they're both the same. So we go down, and this guy's a 1. Cool. So what we do is we take our right-hand side, and we divide this number by whatever this pivot is. It's 1 divided by 1, which is just 1, right? And then what we want to do is we want to make all the rows, all the numbers above and below this pivot equal to 0. Well, there's only one that's above it. So we're going to do some row reducing here. So it's going to be row naught plus row 1 is going to be the new row naught. So now we have a z. This is going to be equal to, so -1 plus 1 is 0. -1 plus a -1 is going to be -2. 0 plus 1 is 1, 0 plus 1 is 1. All right, and because it's in the x1 column, our w1 slack variable is going to be leaving. And we're left with like an x1. All right, and this row does not change. -1, 1, and that still is 1. All right, cool. So the problem that you may kind of see here is, let's make this a green, is if we want to do the simplex method again, we're not done with the simplex method as long as there are any negative numbers in our objective function row. So we see we have a -2 here, but if we go down, we only have a -1. So because this entire column here is negative and there are no other negative numbers here, this kind of tells us that our problem is unbounded. So problem is unbounded. Cool. So at that point, you would really just go and stop, and you would, there's nothing really more you can do. And so that is a linear programming problem solving when it's unbounded.